All right, greetings everyone. Welcome to the first part of the video for section 6.2. In section 6.1 we look at the graphs of the sine and cosine function as well as some transformations of those. In this section we'll be looking at graphs of the other trig functions. So let's start with tangent, and much in the same way that for sine and cosine, we started by making a table of values to try to help us explore what the graphs of those functions looked like. I'm going to do a similar thing here, and unfortunately it's probably going to be hard to squeeze in here because I don't have a lot of space, but we'll see what we can do. So the function I'm going to be working with is f of x equals tangent of x. I'm going to set up a table here using x and f of x. I'm going to plug in some values from the unit circle on this and kind of follow what's in my graph here. So I'm going to do negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. We're going to look at that and see what we get. So if we start with negative pi over 2, we have to think about finding the tangent of negative pi over 2. And we first of all want to use values from the unit circle here. And so in order to be able to do that, we're going to have to break down tangent into sine of negative pi over 2 over cosine of negative pi over 2. And you may also recall, if you think about how the unit circle works and how negative angles works, negative pi over 2 is in the same place as 3 pi over 2. And from the unit circle, we know that the sine of negative pi over 2 is negative 1. And the cosine of negative pi, or excuse me, of 3 pi over 2 is 0. So we end up with negative 1 over 0, which is undefined. Okay, because we can't divide by 0. So it turns out that the tangent of negative pi over 2 is undefined. All right, so let's do negative pi over 4 now then. And we'll again use our trick or our identity that tangent's equal to sine over cosine. And if we again think of these angles in relation to angles on the unit circle, we know that negative pi over 4 is in the same place as 7 pi over 4. And the sine of 7 pi over 4 would be negative root 2 over 2. The cosine of 7 pi over 4, since in the fourth quadrant, that'd be positive root 2 over 2. Notice even though there's stuff with roots here and fractions, we have the negative of something divided by the same thing. And so if you think about it, if we divide something by itself, that just gives us 1, but because there's the negative sign there, we'll end up with negative 1. So the tangent of negative pi over 4 is negative 1. Let's now do tangent of 0. So tangent of 0 will give us sine of 0 over cosine of 0. This one is directly on the unit circle. These values are, right? So we know that sine of 0 is 0, cosine of 0 is 1, and 0 over 1 gives us 0. So we know that then the tangent of 0 is 0. Now I'm not going to go through the next two just for the interest of time, but you can double check me that when we input pi over 4 into the tangent function, we'll get 1. And when we input pi over 2, we get undefined again. All right, so let's go ahead and plot these points then on the coordinate axis that I have here. So I see a negative pi over 4, which would be halfway between 0 and negative pi over 2. So right here, whoops. And I'm also need to put a scale on my vertical axis. So I'll say this is 1, this is -1. So negative pi over 4, -1, that's going to be here. 0, 0 is here. And then we know also that positive pi over 4 will be in between 0 and pi over 2. So pi over 4, 1 will be here. Now at negative pi over 2 and pi over 2, we saw that those gave us undefined values. And you may recall from whichever course you took before this, if you think about rational functions, when we had values that made the function undefined, what we got there were vertical asymptotes. So I'm going to put vertical asymptotes at those points. Okay, and then I'll connect the dots on my other points. And it looks like what we get here, it's not that, because that's awful. So let me try that again. Something like this. So we get a shape that looks like that, which may look a little familiar to you. That may remind you a bit of a cubic function from PreCalc 1. And so we seem to get that shape. And you may think by looking at this that, okay, that's all well and good. That's just what the graph of the tangent function looks like. But recall, as we talked about in section 6.1, that trigonometric functions are periodic. And when they're periodic, that means that they repeat somehow. So that makes us wonder then, what will happen as we move into this area on the graph and this area on the graph? Well, let me show you what happens. So hopefully now you can see an app that I've created on Desmos that shows us a graph of the tangent function. So you'll see here in the middle, we have our that kind of cubic looking shape that we had before. And then you'll see that this green line here and this blue line here, those are our vertical asymptotes. And then notice what happens to the left and to the right of that. Again, because this is a periodic function, we see that same pattern repeating, right? That kind of cubic looking shape there. Okay, so it ends up, this is what we get when we graph the tangent function, this kind of this repeating pattern of these cubic looking functions. And notice also here in my function, I have added this, or put this little form here that's kind of that general form for a tangent function that's very similar to what we saw for sine and cosine, which just allows us then to see what changing these values will do to the graph of our function. So for example, if I change the value of k here, well, we know that that on sine and cosine changed the location of our midline. And we don't quite have the concept of a midline in a tangent function, but do notice that as I slide this, like I increase that value or decrease the value on all the pieces of the function, we see that it seems to be moving kind of that center curve up and down, as we might expect. With adding a value at the end, we know that that makes a vertical shift in the function. As I change the value for h here, as we talked about sine and cosine, that was our horizontal or phase shift. It moves things left or right, and should see that here we get the same thing. Right, so that shifts our function to the left or to the right. And then recall that the value for b on the sine and cosine functions, that created a horizontal or vertical, or excuse me, a horizontal stretch or compression, and also change the period of the function. And notice that we get something like that here. So as I increase the value for b, the tangent function gets compressed. As I decrease, it gets stretched horizontally. And then changing the value of a, we knew from sine and cosine that would change our amplitude. Again, we don't quite have the concept of amplitude with the tangent function, but we do know also changing that value in front would help us to change or stretch or compress the function. And so notice that's what happens here. As I increase, the function seems to get stretched kind of vertically up and down. As I decrease the value, it's getting compressed. And also notice if I change it to negative, then we see a reflection, right? It reflects across the horizontal axis in this case. Okay, so those are all of those, what those things do to this function. All right, I'm going to go back to my PowerPoint here. And I'm going to draw back in the tangent function that we had. So we had, this was -1. So this is where -1 was. This is where +1 was. We had this here, this here, and this here. That. And then we also had our vertical asymptotes. Okay, and I'm going to draw in a couple more periods of this, because we're going to do some analysis now of this function. Okay, and of course the function would continue in each direction. Can't quite draw forever. Whoops, that's not what I want to do. So we get something that looks like not that either. Something that looks like this here, and then this here. Okay, so what I want to do is identify the domain, the range, and the period of the tangent function, just like we did with sine and cosine. Now I'm going to skip the domain for a second because it's a little complicated, but the range, hopefully you see that on all of these, the tails of all of these pieces we see here, they go up forever and down forever, and there doesn't seem to be any breaks in them, telling us that the range seems to be all real numbers, so from -infinity to +infinity. For the period, remember that's the distance over which we see the pattern repeating. And notice that we have one pattern, or one set of the pattern, or copy of the pattern between here and here, another between here and here, another between here and here. And if you look at the distance between those asymptotes, which is basically where that's all happening, notice it's from -3π/2 to -π/2, -π/2 to π/2, π/2 to 3π/2. And hopefully you would agree with me, then what we're seeing is that that's happening over a distance of pi. So our period for tangent is actually pi, which, recall, that's different than sine and cosine. The period for both of those functions was 2π. All right, now let's talk about the domain. And notice that in the domain, right, most values are in the domain, right? So most things between -π/2 and π/2, and everything between π/2 and 3π/2, and everything with 3π/2 and 5π/2, and also go in the other direction. But there seem to be these breaks in the domain, right? At -π/2, π/2, 3π/2, those values are not in the domain. So how do we say that? Well, we can start by saying, and I'm not going to do this one in interval notation. We can say, I'll do x is, and I'll do that funny symbol with this funny symbol. And what this means is this little e looking thing here, it's an epsilon. It means is an element of. Okay, and this funky looking r means all real numbers. because we see that x can be mostly any number we see here. So x can be all real numbers, but there's some restrictions, right? There's some values that x cannot be. So we say x cannot equal, and I'm going to write something down and then I'll explain what it means. So x cannot equal pi over 2, and I'm going to write plus pi times k. And here's what I'm saying there. This pi times k here means whole number multiples of pi. So 1 pi, 2 pi, 3 pi, 4 pi, negative 1 pi, negative 2 pi, those sorts of things. And so what I'm saying when I write this is start at pi over 2. So start at this value right here. Let me erase these. And then add pi or subtract pi to it as many times as you want, and those values are not in the domain. So for example, if we start at pi over 2 and subtract pi once, we get to negative pi over 2, and that's not in the domain. If we subtract it twice, we'll end up at negative 3 pi over 2, and that's not in the domain. If we add pi once, we'll end up at 3 pi over 2, which is not in the domain. If we add it twice, we'll end up at, not there, Cody, we'll be further along. We'll be over here at 5 pi over 2, which is also not in the domain. And we can continue that forever in each direction. So that's why we have that there. All right, that's it for now. Thank you for watching. I apologize. This is such a long video.